Astronomers have recorded the most powerful cosmic explosion so far. It was a gamma ray burst that took place 2 billion light-years away from Earth. It is the closest such event ever detected and was caught by a fleet of observatories both on and above the Earth. The event is already yielding a trove of scientific treasure. The gamma ray burst was so powerful that it affected our atmosphere 20 billion trillion kilometers away and was bright enough to be seen through a smaller amateur telescope. But what are these gamma ray bursts? What phenomenon creates these mighty cosmic explosions? Finally, and most importantly, why was this record-breaking gamma ray burst so crucial to astronomers? A gamma ray burst, or a GRB, is an intense blast of gamma rays. It typically lasts a fraction of a second, and within that duration, it releases as much energy as the entire Sun would in its 12 billion year lifespan. But what is the source of this tremendous energy? To understand that, let's have a quick look at gamma rays. These are the most energetic electromagnetic waves, or the highest energy form of light. A single gamma ray photon could be 1,000,000 times more powerful than a visible light photon. These photons are packed with so much energy that they are a form of ionizing radiation, which means they can strip an atom of its electrons. So they can cause ionizations that can damage our tissues and the DNA. Fortunately, on Earth, the ozone layer protects us. It filters them out before they can harm us. But if these powerful photons cannot reach the surface, how were gamma ray bursts detected in the first place? The answer is the Cold War. In the 1960s, the United States launched Vela satellites to detect gamma radiation pulses emitted by nuclear weapons tested in space. On July 2, 1967, the Vela 4 and Vela 3 satellites detected a flash of gamma radiation unlike any known nuclear weapons signature. Further analysis ruled out the terrestrial and even solar origin of these mysterious bursts. 6 years later, the first paper on gamma ray bursts and their cosmic origin was published. So far, over 1,700 GRBs have been observed, but it took decades to understand better what they are and why they are so powerful. Another challenging thing is that the light curves from each GRB are different. This makes it complicated to understand them as a group. But broadly, they can be classified into short and long GRBs. The short duration bursts typically last a few seconds. They come from two superdense neutron stars packed in a binary system. Over millions of years, their orbits decay due to the energy lost because of gravitational waves. Once they are close enough to touch, they blast out fierce energy, creating a black hole. The long-duration bursts last several minutes and come from massive stars exploding at the end of their lives, again forming black holes. A swirling disk of material that wasn't immediately swallowed by the black hole rapidly forms around it, funneling twin beams of intense energy out into space, one pointing up and the other down, away from the disk. These eat their way through the dying star and erupt outward, while the rest of the star explodes as a very powerful supernova. The power of gamma ray bursts comes from their tight focus. These thin beams concentrate the explosive energy in a very narrow direction. If the beam is pointed towards the Earth, astronomers can see a flash of gamma rays bright enough to be detected from billions of light years. Outside the path, a typical supernova is observed. The recent record-breaking supernova is dubbed GRB 221009A, the first gamma ray burst observed on October 9, 2022. The Fermi Gamma Ray Telescope observed the initial flash in space. It's a space observatory launched in 2008, specifically designed to detect and rapidly find the location of the GRBs. The second burst of gamma rays was caught by the Swift Observatory an hour later. Swift immediately sent out an automated alert to astronomers worldwide, who responded by pointing their telescopes towards the burst. This was an unusually long gamma ray burst, hinting at tremendous energy it had at its disposal. The spectral analysis shows that the GRB originated 2 billion light-years away in the direction of the constellation Sagitta, resulting from the supernova of a massive star ending its life and forming a black hole. Based on the amount of energy released and the duration of the burst, astronomers estimate that the dying star must have been 30 times more massive than the Sun. At 2 billion light-years, it's the closest and the most powerful GRB ever recorded. It even affected the atmosphere of our planet. A tweet by astrophysicist Rami Mandau pointed out that lighting detectors in India and Germany showed how pulses of electromagnetic radiation from light suddenly changed at the same time the GRB energy hit the Earth. These indicate the conditions in the Earth's upper atmosphere changed, with electrons suddenly stripped from their host atoms. Although the change was mild and brief, considering the 20 billion trillion kilometers between the Earth and the source of GRB, it's an extraordinary phenomenon. This GRB is an exciting discovery for astrophysicists studying high-energy cosmic phenomena. It's so bright it will take months for it to become too faint to see with telescopes, meaning astronomers have time to study it. But there's a problem. At the end of November, GRB 221009A will be so close to the Sun that astronomers won't be able to see it through their telescopes. So they have a short window to study the initial glow of the GRB in multiple wavelengths before it goes behind the Sun as seen from the Earth. When the GRB 221009A emerges from the other side of the Sun, the astronomy community will be able to continue to track its afterglow to constrain the jet opening angle of the GRB and thus get a handle on its true energy. Astronomers still need to figure out why this particular GRB is so bright, but they believe a multi-wavelength analysis will indeed decipher this mystery. It is also theorized that the most energetic GRBs could be burst sites of some of the universe's heavy elements. This gamma ray burst serves as an unprecedented laboratory to test that theory. Astronomers want to see if supernovas can synthesize heavy elements such as gold. So they'll measure the spectra of light emitted by material blasted away by the supernova that created this particular GRB. Studying gamma-ray bursts is important because they serve as excellent laboratories of the universe's most extreme processes. And astronomers are thrilled because they may have witnessed history in this once-in-a-century explosion. This concludes the 35th episode of the Sunday Discovery series. So if you've enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any future videos of the series.